All right, ladies and gentlemen. So you guys can do quite a bit now with logs. We know the purpose of logs. We know how to convert logs into exponential form. We know how to approximate logs. So we know how to think about logs. We know how to deal with difficult evaluating problems, easier evaluating problems. When problems don't evaluate, we can actually tell you which two whole numbers are in between. And we just covered two basic log properties about how exponentials and logs and how they undo each other if their bases are the same. Okay, so that's basically everything we've talked about to this point. Now we're getting ready to start solving stuff, and in order to solve stuff, but let's take a pause here, and I want to recap an issue that we had back in the day. Okay, and that's the domain. All right, so if you remember, recall domain, which is all possible inputs. Recall that if we're looking for the domain, all right, this is all possible inputs, so all the x values that can go into any of our functions. Okay. And then we knew that in order to find the domain, we can't look at every number that works for it. There's just too many on the number line, right? It's easier to look for the ones that don't work and then get rid of those. So we looked for the domain restrictions. And then in the past, these restrictions, one was if we had a denominator. And if you notice, there are similar themes all throughout, I don't know what that was about. That's pretty interesting. Denominator. So the domain restrictions, like the denominator has been a theme throughout all of them. So you saw like the denominator being an issue in when we were doing sign chart stuff, right? Because the denominators created bad numbers, right? So it's the same stuff. And you're going to see they're the same thing when we get to 1800. Like they'll call them something different. They're actually going to be called vertical asymptotes in 1800. Fancy name. All right. So denominator can't be equal to 0. That was the first restriction. The second one was if we had an even root. So if we had an even root, then the radicand, so I'll put this, if this happens, then the radicand, which is the thing underneath the root, could not be negative. If it can't be negative, it must be positive, which is greater than 0 or equal to 0, okay? So the new guy is this one, okay? And that is if a log appears, we'll say a of b, so if you have a log appearing, and this is the new one, and I'm going to explain why in a second, then the argument, the b part of it, that thing must be strictly greater than 0. Okay, so that's just the facts. Now let's talk about why. All right, so why does this make sense? Okay, so let's consider this. So why? Okay, well, consider log base 2, okay, of x. Okay, and we're trying to see which numbers we can plug in for x, and I'll call this my function, right? Since we're talking about domain right now. So I'll make a t-chart just to make things easier so we can keep track of things. Okay, so easy peasy. Let's try some numbers we're comfortable with, right? So let's try 2, right? So log base 2 of 2. 2 to the first power is 2. 4 is another good one, right? Because that's 2. 3, sorry, not 3. 8's a good one, right? Because now we know that 2 to the third power is 8. So the way we're thinking about this is backwards, right? Well, what's the next good one? Well, that's 1. Why is 1? Because we got to have 0 accounted for. So if you look at it, right? But hold on. Well, what about 0? Can I have 0? Maybe. Can I have 0? Well, I don't know. Let's see here. Sidebar. Log base 2 of 0. What is that? Well, I could say 1 because don't 0 and 1 have a question, but hold on a second here. Let's convert it and make sure, okay? So here's the thing. If you're ever lost, you just convert it and then stop and think about it, right? Why? 2 to the blank equals 0. Well, hold on a second here. If 2 to the 0 power can't be, what do you mean? If this is 1, 2, 3, we get whole numbers. If this is 0, then this should be 1. If this is negative, it should be a fraction, okay? So it doesn't ever become 0. So this is not possible. All right, so that's weird, okay? So this is not possible. All right, so if that's not possible, now it's something that's tricky here. All right, well, let's see if we can find some stuff in between here. And that's why I left the space here. Well, we are talking base 2, right? So think about the answers that have good base 2 answers. How about a half? So 2 to what power is a half, right? 2 to what power is 1/2. That's right, -1. Interesting. So 1/4. That's also a good one too. It's -2. Oh, so remember, we're looking at all the inputs, which is this category. Okay, and it looks like I can have positive whole numbers. I can have fractions that are also positive, but I can't have 0. 0 is not possible, but everything in front of 0 is possible. So what does that mean? So for a log restriction, this thing in here, which is the B part, has to be greater than 0. And that's all it is. No ifs, ands, or buts about it. So anytime you see things like log base, 2 of 5, that's okay. It's ugly, but it's a positive number. If that was a -5 though, no good. If it's 0, no good. It has to be greater than 0, only positive. And that is the point, okay? So the argument, so moral of the story. So here's the moral of the story, okay? The argument, which is the B part of the log, must be positive. Big deal. Big deal, guys, all right? So let's go ahead and do a quick example or 3, and then you'll get to see what I'm talking about, okay? And then it makes perfect sense, at least I think so. But after all, when don't math teachers say things make sense and they really don't, all right? So let's take a look at it. So those are the 3 restrictions, all right? So let's be very basic. Here we go. I like my black pen when I go into examples. Now, sometimes you just like things the way you like it, right? So my thing is I just like it like this. So here's an example for you. Let's say it said find the domain. And I'll keep it real simple, okay? And it says f of x equals log base 4 of 3 minus x. Right? Now, it's not asking me to solve it. It's asking me to do anything to it. It's asking me to find its domain. Okay? So you need to know the domain restrictions, and you need to know these 3 that are right here. So does it have a denominator? Does it have an even root, or does it have a log? So you're just going down the checklist. So in your mind, you're saying to yourself, okay, so here's your brain again. I'm not going to write it on paper per se, but I'll write it in your brain. Here's your brain. Okay? And in your brain, you say to yourself, does it have a denominator? Okay? No, it doesn't. Does it have an even root? No, it doesn't. Could you have more than one? Yes, but you don't in this case. And do you have a log? Okay, yes. All right, so here we go. Here's the log guy. I'm going to set it up. So that means the argument. That means just the B part. Which part's just the B part? All right, that's just this part. So there's the stuff that's in the argument. I don't care how complex it is. 3 minus x must be strictly greater than 0. Okay? So now, what that means is can you solve that? Absolutely, I think you guys can solve that. This is going to give me -3 here. And remember, when you multiply or divide by a negative, you flip the sign. So this gives me x is less than 3. All right? So, what's my domain? Let's draw our picture like we always do. Here's 3 and everything behind it. So I'm going to have -infinity to 3, soft bracket. There is my domain. Easy peasy. So you just have one more restriction to put in the mix of things, okay? Let's do a little bit more of a difficult problem. Let's put multiple restrictions in there, and then we'll marry everything together and make sure it looks beautiful, okay? So here's another good one. This incorporates some of the old concepts we had from section 8.9, which was sign chart stuff, okay? Which was solving nonlinear inequalities, right? We always say sign chart like that's the problem. No, that's what we use to solve nonlinear inequalities. All right, so here we go. Find the domain. All right, so I'm going to find the domain, and here's the function, and here's the function. G of x equals log base 10 of x squared minus 3x plus 2. Okay, well, all right, yeah, it looks a little juicier. Now they're looking for finding the domain, and you go down your checklist, okay, and again, what's your checklist? Well, do you have any even roots? No. Do you have any denominators? No. Do you have any logs? Yes. All right. Now, since we have a log restriction, let's deal with the log restriction. Okay. So the log is the restriction, and so I need the B part, which was x squared minus 3x plus 2. We want that B part to be strictly greater than 0. Okay. Do you know how to solve this? Yes. It is a non-linear inequality. Don't you dare do one of these. If I see this, if anybody sees this, I'm pretty sure they're going to mark everything wrong. I know I would mark anything wrong. There would be no partial. The whole world would bleed points. Oh my goodness, be dramatic here. If the minute, so the factoring is good, here's what's bad. X minus 2 greater than 0, x minus 1 greater than 0. The minute you do that is the minute the problem is done for you. Okay, there will be no more partial credit for you. There will be nothing, because that's trash, okay? Because this, and this is where this takes over. The minute, come on, my highlighters, you're making my drama leave. The minute I see an inequality and it is nonlinear, the minute this happens, then this takes me back into section 8.9, and I must make a sign chart. Okay, it's non-linear to degree 2. Okay, it's not a mx plus b guy. Don't you dare try to do it. As a matter of fact, as a minute you see an inequality, don't even think the old way. Just think sign chart immediately. Okay, because now it's a tool you use within problems. Okay, so now to solve this, I need the zeros. So when I set them equal to 0, I get x plus 2 equals 0, x minus 1 equals 0. Again, all right, so x equals 2, x equals 1. Okay, and then I don't have any denominators within the inequality. Nominators. And now here's the thing that is so important. So I don't have any undefines. So I don't have any of these. So I have none. Okay, but here's the thing. I'm not looking at the entire problem. This is the only problem I'm looking at. This is like a little sub-contained problem by itself. So then when I get more and more restrictions, I'm looking at it. So a denominator in this mini section is what I'm looking at, this log part. I'm not looking at the entire problem. That'll be taken care of somewhere else if it appears. So I'll show you in the next example. Okay, so now let's rock and roll here. So now, here we go. Let's go ahead and let's put our numbers on our number line, right? Our sign chart, and let's label them. They are zeros, okay? When you plug in numbers and you test points, I'm getting positive, negative, positive, right? Because of negative times a negative, a positive times a negative, and a negative times a negative, okay? Now they're looking for one they're strictly positive. So that tells me that my answer to this inequality is going to be all of these positive guys, but not the zeros, because I must be strictly greater than 0. Now, if I had more restrictions to solve, I would solve them, and then I would have to marry them all together. But since this is the only restriction, this is the domain. So the answer would be negative infinity to 1, soft bracket, union 2 to infinity. Really all that is, okay? Just remember, anytime you have a nonlinear inequality, that you must make a sign chart. It could be tricky or not tricky. All right, so this one's a good one. I'm going to go through it with you, and it will come up probably for the remaining time, okay? But it's a very, very difficult problem. If you can handle this one, you can handle any one, okay? So here we go. All right, so I'm not just going to give you one additional restriction. I'm going to give you 2 restrictions. We're going to marry it all together. So here we go. We'll call this bonus difficulty. On a scale of 1 to 10, this is a 15. Okay, so but if you can manage this, you're good. So find the domain. And then I'll talk about style. I'll talk about, given all the difficulty, where to actually start. Okay, so first things first, this one appeared on a different final. I'll tell you the final at the end of when we get done with the problem. That way you guys can all know which final it came off of. I have to look it up. All right, here we go. So you look at this and you're like, okay, it says find the domain. And by the way, we didn't say this, but I'm hoping you figured it out by now. Okay, ln, because I don't believe in just hand feeding you guys everything. I do believe you need to Google some things. You need to use your resources, because if you don't know how to use all of your resources, then game over. It could be a disaster, okay? So ln of something, I don't know, you call it something, is the same thing as log base e of that something. Now, what's e? E is just an irrational number like 2.71 and some change, okay? So what that means is that, think of it like pi, just another irrational number. So it's no biggie, but bottom line is when you see ln, it's a log. So therefore, it's a log restriction, all right? So you'll notice we have all 3 restrictions here. We have even roots, we have denominators, and I have a log restriction that all must be taken into account. So let's handle all of them one at a time, okay, and very meticulously. Okay, the more restrictions you have, the more problems it adds in, and more difficulty it adds in. But nonetheless, it's all the same stuff. Okay, just got to keep track of it and not make any boo-boos here. So my paper's all set up. Remember, pretty paper means you're going to want to look at it. Okay, so this is the log restriction. Okay, that means that I'm just going to set it up. I'm not solving anything. That means just the b part, the x squared minus 4x minus 5 must be strictly greater than 0. Just the b part. Okay, so a of b. So if that b is strictly greater than 0. That's what we did. All right. If you have an even root, you guys should know by now, only the stuff underneath the root, the radicand, should be greater than or equal to 0. Okay. And bottom line is we have a denominator, and the denominator cannot be equal to 0. All right. Now, if we can grind through this, life is good. All right. So here we go. I'm going to do the log one last. Why? Because I'm thinking it's going to be a lot of work. Okay, so I just want to get the other ones out the way. Because starting momentum is always a good thing. So x can equal 4, that's easy. So that's one number I don't like. It's got to go. Okay, also, the even root says that x must be greater than or equal to negative 5. Okay, so now there's a whole bunch of other numbers I got to get rid of. All right, let's see what this picky guy does. And again, that was a linear inequality, so I could just solve it directly. This guy's nonlinear. So I need a sign chart. You don't do a sign chart. You don't do points on this one at all. All right. There is no partial credit on stuff when you're confusing concepts. Conceptual errors are major point losses. Okay. Miscalculations are minor things. Now, minor things can add up, but a good way to get a minus 10 is a conceptual error. Okay. So watch your conceptual errors. Okay. So I'm going to factor this guy out, same way we would do when we're making any other sign chart. Okay. And that factors perfectly. All right. So here we go. Zeros are x equals 5 and x equals minus 1. If you guys solve for your zeros, your undefineds, there's none since there's not a denominator. Okay, sometimes there could be a denominator. Don't just think there's never one. Okay, because there could be a fraction in this log, right? X plus 7 for example. Okay, so now let's make our sign chart. In our sign chart here, I got minus 1, I got 5. These are both zeros, but I don't want to include either one of them because it says I must be strictly greater than 0. Okay, so again, we are not making any of the equations. The only place, if you notice, anywhere in this work that you see an inequality is right here. It's not even in the work. Okay, it stops there. So, this thing, I'm looking for when it's positive, so I got to know when it's positive. Well, when you plug in numbers, and I'll spare you the details into this function, you get plus, minus, plus. Okay, so it tells me the positive things are on the outside. So I want it this guy on out. I want this guy on out. Okay, those are all the numbers that accommodate just the log restriction. Now we also got to blend that with this guy and with that guy. So it's a lot of things to blend, but it's okay. We can handle it. All right, so I'm going to draw another number line, and what we're going to do is we're going to blend the first two together. And then once we get a blended picture for that one, we'll do a final blended picture. Okay, so here's negative 1. Here's 5. And then the blue guy says, okay, I like this on back. I like this on forward. Okay? The even root comes along and says, hold on though. If it's negative 5, here's negative 5. It says, I like negative 5 because I can be equal to negative 5, right? I can be equal to it. Okay, but I like everything that is bigger than x. So now your job is being the whatever of the house, the major function of the house, the major breadwinner of the problem, whatever you want to call it, is to figure out, well, how does it accommodate the entire family of people? And then we got this person in the corner that's x can equal negative 4 that we just got to throw out negative 4 in the end. So if I had to do this thing, if you notice, there's overlap from here to here and from here on up. So from negative 5 to negative 1 should be this overlap. Okay, but at 1 it won't be closed, it'll be open. Should be this overlap, and from 5 on up. Okay, so that's where we're at so far. That's in stone. It's no longer a blue light of imagination. We actually know that's right. Now let's go to our green guy, which says throw out negative 4. So if I throw out negative 4, then that means this is going to have a bullet hole at negative 4 as well, but everything else should still be included. So there's my domain. Okay, now we just got to write an interval notation. So I'm going to need 1 interval starting at -5 going to 4, picking up on the other side of 4 going to -1, but not all the way past -1 or equal to -1, and then picking up at 5 and going to infinity. So this is the domain of my entire problem. Okay, so again, it is hard, right? Not really. It's just tedious. And you'll notice things just consume more of your time. There is no harder or not harder. The only reason things are harder is because you decide to move faster and try to do it at a faster rate than normal people. That's what I've noticed, okay? If you get the normal rate at which things are supposed to be doing, you give things the time it's supposed to be doing, it's not harder or easier. It's more time consuming or not. Okay, so just slow down, be more meticulous. This guy's for sure more time consuming because you have to wait. Your hand is the ultimate slowdown, right? So as you're practicing these things, make sure you slow yourself down, be patient, and try to stay in the problem longer. Einstein said one of his major realizations in life wasn't that he was smart, is that he just didn't give up. He stayed in the problem longer than anybody else. Okay, so I'm going to encourage you guys to do the same thing. All right, when we come back, now that we know that logs, the arguments can't be equal to 0, we're in a position to actually start trying to solve some equations. So we'll start section 9.6 next time. All right, guys, I'll see you guys in a bit, and see you on the next video. Adios.